Let's welcome to the stage Michał Chodzikiewicz.
Hello, everybody. So the introduction of myself was quite elaborate. I kind of regret my my writing, maybe a little bit. Okay, but anyway. So as you can see on the first slide, it says future is memory safe. And maybe you noticed that this is not the title of my presentation. Actually, this is more of my wishful thinking, as well as dream of rewriting everything in Rust. No, just joking. But maybe a lot of you, or some of you, are tired of people who have strong Rust advocacy because of them being loud about it. But what I want to show you today on the presentation is that it is not only about what style of programming you like, what tooling you fancy, and so on. This is a bit more important thing. Okay, so who am I? I am an embedded Rust developer. I work at Klikatech. Also, I am Rust Wrocław meetup organizer, and I warmly invite you to join. We have meetups more or less monthly, maybe sometimes 2 monthly, something like this. But anyway, we did a lot of them. I think the counter is now at 35 meetups over a couple of years. So I believe we are the biggest Rust community in Poland. I have GitLab and GitHub where I do some minor open source developments you could check out. I have Mastodon, also called Twitter for Nerds. Yeah, this is, I should have told this at the very beginning. I might want to try to make you cringe at some point. So beware. It is not necessarily that I giggle at these jokes and memes when I fall asleep. Okay, if you want to reach out to me about Rust, I think the best place would be Rust Wrocław Slack. You can also meet a lot of very nice people over there who might be even way better experts on Rust than I am. Okay, back to the ground. I think future needs to be memory safe, and let me tell you why. So, at the end of last year, NSA published a document, like recommendation for memory safety issues, and in that report, it says, let me read it out loud. Microsoft and Google have each stated that software memory safety issues are behind around 70% of their vulnerabilities. Poor memory management can lead to technical issues as well, such as incorrect program results, degradation of the program's performance over time, and program crashes. NSA recommends that organizations use memory-safe languages when possible and bolster protection through code hardening, defenses as such compiler options, blah, 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 blah. Okay, the when possible part. You might say that, well, but it's not possible in certain areas, like, for example, very constrained devices, like microcontroller stuff, and so on. But this is actually not the case anymore. At least this is my thesis here. Yeah, but why this matters so much? Combination of these two things prevents me to sleep at night sometimes. And it is direct access to hardware without any isolation, like from operating system, and internet connectivity. This is like exposing everything bad in embedded development to the internet, which is even worse. So it was funny, like 10 years ago, that on the Internet of Things, nobody knows you're a fridge. Right now, it is not funny. It is maybe pretty scary the other way. So it is kind of scary that on the Internet of Things, I have a fridge. So, you know, a bad actor could do very horrific things with your home commodities if they are internet connected. So for this exact reason, as a consumer, I really, really, really want improved security in this area, right? Actually, some of you might agree, some might not, but personally, I want some regulatory bodies to force better security, because we all programmers are lazy bastards and we don't care about humanity. But I am a developer, and to achieve this goal, I need something that will help me with this. And this leads us to the title slide of this presentation, which is Fairless Firmware in Rust, and why this matters. So, yet another quote, pardon me for this, but this one is not from NSA. This time it is Consumer Reports. So this is US organization, NGO, I believe, that is more in consumer side advocacy, so it feels more important to me even than NSA recommendation. So they, in their report on memory safety, they say more or less the same things as NSA, but this is the thing that caught my attention. The lowest hanging fruit for memory safety is brand new code. But to be successful, we must recognize that some programmers may find memory safe languages more difficult or be resistant to shifting to them. And you know, where I believe there is a very frequent occasion on developing a greenfield project where you can start from scratch and build a system, it is actually a microcontroller project, because your technology stack is very small because of small footprint of your program. So this is easy target to start on. Actually, I believe it could be easier to find a greenfield project in microcontroller space than in like big distributed cloud systems or whatever. So let me do very quick recap on Rust, and this is only about a single property of Rust that is crucial for the security context. And this is that you need to obey ownership model. So the borrow checker won't let you leave if you don't care about ownership model. So what does it mean in practice? In any scope in program where you create an object, you can only either move this object to a different scope, passing the ownership to a different scope. You can, or you can pass the immutable references to as many scopes as you like. So you can access immutably your object in many places, or, but this is excluding or, you can create a single mutable reference that you can borrow to one scope, and then this part of code can modify your object. And only when the lifetime of this borrow ends, you can, for example, immutably borrow this to different parts of your code base. Okay, and if you don't do this, the program will just not compile. And this might sound to you like this is not a big deal, but this is a huge deal, because this is a contract that is passed to your entire code base, and it allows you to introduce abstractions that are impossible in most other languages, especially if you look at mainstream languages that are natively compiled and without garbage collector. Okay, but if you have this restriction everywhere, you cannot do really that much about your program, right? Because how to do most of the things in a bigger program, you need you need to access concurrently to objects and so on, right? So this is why in Rust we have unsafe blocks. Many of you, or I mean maybe not many of you, but there is a misconception popular in the internet that you could, for example, just write unsafe at the top of your source file and finish the block at the bottom and write what would be more or less like a C-style code that have no safety benefits at all. This is not true. Actually, this only leaves certain properties, certain safety guarantees, and what we need to care here is only one, which is row pointer dereference. So you can even pass row pointers in a safe code, but you cannot dereference them. And this is basically for our purpose today, at least. This is the only thing you can achieve using unsafe block. So, and if we go to intentions behind the unsafe block, this is more like, I swear to you, dear code reviewer, that what I have done here is as small as possible and correct, and it was impossible to do it in other way. And you can also view this like, if you write unsafe code, this is a challenge to reviewer to prove you that it could be written in a safe code. But indeed, there are some parts that needs to be written as unsafe blocks. And you can find a lot of this in standard library. So where you can find it, for example? You can find it in implementation of smart pointers in Rust. So let me maybe start from the last point of the list and not the first one. I'll tell you why in a second. So we need to, if we want to call C functions, which we can do in Rust, and this is quite convenient, we need to do this inside an unsafe block, because C is not safe language, and we don't know what happens there, so we need to guard access to these functions with an unsafe block. And if you think about it, this means that you have to write an unsafe block for basically any interaction with, for example, operating system, because you need to do some syscalls, and usually you do syscalls via glibc or muscle or whatever library you use on your target that will wrap the row syscall routine into a C function. So if you want to, for example, allocate something on a heap, you need to call an unsafe. But what we do in Rust is we encapsulate these unsafe blocks inside functions that are safe. So inside such a function or type or whatever, we encapsulate this small unsafe bit, but we do not expose it to the user. And our responsibility is to make it sound and correct. And if you think about Rust standard library, it is quite widely used, so you can consider it safe. Also, there are some efforts to mathematically prove unsafe parts that are way more extensive than what borrow checker can achieve. Yeah, so for example, boxt is just heap allocation in Rust. So if you want to allocate something on the heap, you just create the type you want inside a box. That's all it is. But because you need to allocate some memory for it, internally this will have an unsafe block. You also have like a ref cell, and this is basically a type that will allow you to postpone the borrow checking rules until runtime. So it will not allow you to do the mutable borrow if you have immutable borrow at the same time, but this will not be enforced at compile time because sometimes it is impossible. It will be checked at runtime. And to lift the borrow checker restrictions, you need to use unsafe, obviously. and then you re-implement the same mechanism, but on runtime. Okay, you also have RC and ARC. These are like shared pointer in C++, so this is like counted references. Nice thing about them is that you have RC, which is reference counted pointer that you can use within a single thread, but if you need to pass these references across threads, you have ARC. And they have the same API, but RC is optimized because it knows that it will not be sent across the threads. And nice thing about Rust is that it will be enforced at compile time. So if you use RC across the threads, it will just not compile. And then you will just know that you need to substitute RC with ARC. So I think this is a nice quality of life, because by default you get optimized version of it, but you can opt out and send it across the threads. Another thing that might be worth mentioning is lazy static. I think it might you might not need to use this crate anymore, but this is very common to see. What it does is that you can create like a static object, but it will not be initialized like in C++, for example, where you have this deterministic but unknown order of construction. So it can lead to, for you, if you for example have a reference to another global object in your different global object, and in a constructor you call a method on this object, it is undefined behavior. So nice solution for this in Rust is to use lazy static, which means that when you first access this value, it will be initialized by the code you provide for its initialization. This is very convenient. Okay, the last point was already discussed as an introduction to this. Okay, but we are here to talk about firmware, so we don't even have an OS, so what are you talking about, right? Come on. What I want you to do after this talk is maybe not to decide that, okay, from now on I am going full Rust for my microcontroller projects, but what I want to do is to give it a try, to have a look, what's there, and maybe you can explain this to your beloved C++ or whatever you write in, and she will understand, right? Okay, let me show you how typical microcontroller project looks like in Rust. So it was very fortunate that when Rust was quite a young language, it already had some community that was focused on bringing it to embedded. Even though these were very rough times, during these early stages, some common APIs were introduced, and entire community agreed that yes, this is the place where we will develop embedded ecosystem. And if you have experience with C or C++ development for bare metal systems, usually what you get is vendor-provided hardware abstraction layer library that varies in quality, but most importantly is incompatible with any other chip from a different vendor. There are loads and loads of ecosystems that are not compatible with themselves, which means that there is a huge fragmentation. However, in Rust, all the efforts are focused in basically a single working group. However, very welcoming working group, so if you have ideas, you can join them and discuss them. It is not like behind the closed doors or whatever. Okay, anyway, what embedded HAL organization does is in a set of crates, this is not a single crate, they introduce traits, which are like APIs for accessing common hardware peripherals. And this is great because this creates this common point for both hardware abstraction layer authors and also device drivers authors. Okay, but before we go this high in the stack, first we need to have peripheral access crates. And what this is basically memory map of your device, because all your peripherals in microcontrollers are usually memory mapped. So ARM introduced a standard of expressing where given peripheral is in your chip, and in this format you create entire map of all peripherals in the chip, and you can use it to generate code in whatever language you like. So PAC crates or peripheral access crates are basically automatically generated from these SVD files, but this is not ARM only thing. This received quite nice adoption also in different architectures. So what you get there is set of structs and places where the structs are. So like a bit like a set of singletons that are safe to access, because you need to synchronize access to these registers, and this is all done inside the PAC crate, and this is automatically generated. So if you have SVD file, you can just bring support for Rust to your target. This is quite nice. The next layer we have is hardware abstraction layer, and what is being done in this part of your code, of code you use, is code that you can use to correctly initialize the peripherals, and then you get implementation of embedded HAL traits relevant to peripherals you have on board. And finally, there are device drivers. They typically only depend on embedded HAL. This is still a bit painful thing, but this should stop to be a problem soon. So embedded HAL is still not released in 1.0 fashion. It is still a point release plus release candidates for 1.0. So this makes a little problem that there is some kind of fragmentation in the ecosystem, but this is manageable, and this is a great opportunity also to maybe contribute to some open source projects, because it is relatively easy to port to a newer version. This is what I did a couple of times, and this is quite nice experience. Okay, but anyway, these are the building blocks of your basic Rust microcontroller program. So what we do? First, we do obtain our peripherals from PAC crate, which means we take ownership of this peripheral, and this is very important for Rust being a safe language in this scope. We use HAL methods to configure our peripherals to desired state, and this is also done in, for at least for me, a very smart way, which I will show later. And then we use the traits, and we utilize our I/O directly, or we just pass it to the drivers with hope that drivers are using the same version of embedded HAL traits, right? Okay, but let me show you how it looks in the code, but it will be a relatively simple example. So how does obtaining peripherals look like? So this line tells you that we create a mutable peripherals object, and we take this single instant that can live in safe Rust from our PAC crate, which in this case is STM32F401, which is a very popular chip. So we take these peripherals and we can use them in the scope we took it. And if we take it yet another time, we will receive an error, because here you can see an unwrap, and unwrap is, I don't care about error handling, I just want the thing, and it can lead to panic. But in this case, I think it is okay to use it instead of error handling, because usually you have a single point where you would like to obtain your peripherals. If it's not the case, you're doing something wrong and you will receive runtime panic. Don't do that. Okay, so now we have our peripherals in scope. And what we do is now we can split this big object into smaller chunks, and use it in different scopes. So we can pass it over throughout our entire program. So for example, a single task can blink a LED in GPIO 8.5 pin, for example, and a different part of program can handle UART and so on. What is very nice, and I briefly mentioned about it, is type state pattern in embedded ecosystem, especially. So what is important in this code snippet is that in the second line, we configure our clock to use 8 megahertz crystal. And then we call a freeze method on this. What we freeze here is not the clocks. It is freezing the configuration for the clocks. So until we unfreeze these clocks, these won't change. And we have clocks object, which configuration is frozen, right? So we already have some guarantee that is not that easy to achieve in outside of Rust. Okay, then we take two GPIO pins. One will be our transmitter pin, and the other will be receiver pin, because this is UART configuration. Then what we do is we configure our serial port, and what we do as a first argument is we pass ownership of TX and RX pin to this UART instance, to this particular peripheral. So we no longer can use these pins anywhere else. These are held by this serial. So no accident reinitialization or this kind of stuff. And then we have config. We freezed the clocks. This is what I already told you. And now we have something that is clock related, and this is a baud rate, because this baud rate calculation of all the registers we need to write some values in are dependent on the speed of the bus. So if we change the frequency of this clock, it would alter the baud rate of the UART. And because we do this, and maybe for some other reasons, we immutably borrow clocks. And since these clocks are borrowed, we can no longer unfreeze the clocks, because it would be mutation of its state, and this cannot be done until we unfreeze. So if we pass clocks, because it is immutable, we can pass it to many peripherals, but we cannot change the clock configuration until we uninitialize all the peripherals that are using the clocks, and only then change the speed of clocks, and then maybe reinitialize the peripherals once again. So this is nice safety mechanism, especially being a young software engineer. I shot myself in the foot a lot times, just copy pasting code here and there and reinitializing the same thing couple of times, and this was very frustrating to debug. After some time you get used to it and you don't make these mistakes that often anymore, but it still happens from time to time. So here it is impossible, and this is like thing that is very important for me. Okay, now I will show you, maybe I hope this is big enough, but we will just quickly go through it. This is AtCommandDriver. It is using any basically serial port, and you know AT command protocol. This is used for modems, like GNSSs. Basically, quite widely used in radios and this sort of stuff. But anyway, this is basically sending strings over UART, but they are specifically formatted. So what we can do is we can pass our UART to the AtCommandDriver. It will take ownership of it. But what you may already noticed in this code, that we do some static objects in global scope. And what this means is to access it, we need to do some unsafe things. And this is quite displeasing. It gets even worse when we take a look at interrupt routines, because it is unsafe all over the place. So I don't like it at all, but this is how it looks when you use just a runtime crate for your microcontroller and a HAL and a pack and nothing else. I don't like this way of coding. I would suggest all of you to reach out for some kind of a concurrency framework. It will make things a lot easier. I will only mention here one such framework, which was more popular some time ago, I think. Right now, there is a new shiny thing in the neighborhood, which is called Embassy. But what I will show you, okay, so just a thing. What you maybe know about embedded systems is that even though we don't have threads as operating system abstraction, interrupts are basically like threads if it comes to memory safety contracts, because they can just preemptively stop your normal code from executing and start executing something else, and then resume the execution. And this means we have concurrency problems in interrupts. So just for simplicity, this is nice bold statement that interrupts are threads. And you know, Rust is thread safe language. So we can leverage memory safety rules in Rust to have hardware safety, let's say some sort of hardware safety, because because if we obey the ownership model, we are fine with concurrent access to resources between interrupts and main thread and whatever. Okay, so there is this Artic. This is real-time interrupt concurrency frame. I don't remember, honestly, what the abbreviation is. But this is a bigger gun. It basically wraps your entire code into what I would call like a bit of a container. And you can look at it either as an RTOS, because it is preemptive, or just a thin wrapper on a thing in ARM, which is called NVIC. So NVIC is Nested Vector Interrupt Controller, if I remember correctly. And this is a hardware mechanism for prioritizing the interrupts. And what is very fancy about Artic is this is basically a wrapper for this peripheral, but it uses it in a very funky way. That is quite smart. Okay, how the Artic app looks like. We have, this is basically the entire minimal program. What we have here, I will tell you in the details in the next slide. We have only like handful of things. This is like shared structure, local structure, init function, idle function, and tasks. Okay, but first let's look at the macro. By the way, macros in Rust are nothing like C macros. This is much safer, and I wouldn't dare to say this is more powerful, because you can do anything with C macros, but this is way better experience to do it. And proc macros like this one, I won't dig deep into it, are basically a bit like a compiler plugin rather than dummy text substitution. But anyway, this macro have arguments, and first argument is a device, which is a pack crate that we will use. It will take ownership of it. And the second thing is dispatchers that we want to give control to Artic. And this is because Artic will use unused interrupts that you don't use for your hardware interrupts. It will use it to do priority-based scheduling for your software tasks that will be triggered by software. So as many interrupts you don't use on your microcontroller, that many level of priorities you can have in your soft tasks, and I mean preemptiveness priority. Okay, so resources. We have shared struct, which contains a single field, which is counter shared. Now that I have seen all the presentations here, I would write it that we have shared propulsion engine and also local propulsion engines, but it's too late already. But it should be something more spacey. But anyway, yeah, we have shared counter and we have local counters. Then we have init function. In init function, we initialize both these structures. I am quite short on time, so I will not dig that deeply into it. And then we have idle task, which does nothing. You can omit this at all if you don't need idle task, but you can also do like an infinite loop in there that will do some, let's say, least important stuff in your program. Okay, let's see at a hardware task. This will be triggered each time a USART2 interrupt will be triggered. And this interrupt only uses a local resource, which is counter UART, and access to this resource is, yeah, you just call the context structure local counter UART, and you can do any operations on it as is. You just need to dereference it to increment it and then to print it. Yes, so now we have a software task, and this one also has a shared resource. And the difference here is that when we have a local resource, we can access it as is. But if we want to access a shared resource, we need to do this via Mutex. And this is, Mutexes in Rust are very nice because how they work is these are type wrappers for your objects. So to access it, you need to lock the mutex, which means you run a closure or lambdas, fellow C++ friends. Yeah, so you do your modification operation or any kind of access inside a closure. You cannot do this externally because it won't compile because of the borrow checker. Yeah, and then you can leave the scope of your closure and continue. Okay, now there is a software task 2, which is basically the same. I might want to mention here just DFMT. This is second important line, second that has some letters in it, second from the bottom, I mean. So there is DFMT info, and what DFMT does, it is very nice because this is very cheap way of printing debug things in your application. Why this is very cheap? Because, very quickly, what it does is it creates a fake section in your elf file that will not land on the target, and it will contain all the string literals that are used in this print. And what will be sent over the debug wire will just be a reference to this string that have not landed on a microcontroller flash, and it will also pass the values that will be used to format, but the formatting itself is done on host. So this is extremely cheap, and you can print from everywhere and not be bothered with performance issues you get when you print strings, long strings over the wire. Okay, this was just a thing that you might like about it. Okay, this was very brief, but I guess it was impossible to dig very deeply into it. I just want to boost your curiosity here. Please read Artic Book. This is very good read on what design choices were made and how it is like. If you stick to safe Rust, it will just make your experience flawless. Okay, but before reading Artic Book, which requires you to have some grasp on Rust, before it, read Embedded Rust book, and even before this, also read a Rust book, which is great read, and I think maybe you have already seen this somewhere. In general, documentation for Rust is quite comprehensive, and communities around some different topics usually create quite nice documentation. So please give everything here a read, and I will just hint you some more stuff. One is Embassy. It was covered by Cesar, who had a talk before me. This is like async runtime for NoSTD, so it allows you to write asynchronous code on bare metal target. This is very nice, and this is getting a lot of popularity right now, to the point that Rust newcomers might not even recognize Artic because it is no longer that hot topic. DFMT I mentioned briefly. FlipLink is a very nice thing that will allow you to link your application a bit differently. So instead of overwriting your static variables, it will your stack will grow towards end of the memory region. So it will lead to hard fault instead of undetermined state. So basically undefined behavior. Then there is a probe arrest, which was also mentioned already on this conference, which is great. I used it not only to just flash your microcontroller, I also did some dedicated programs that would flash microcontrollers in very specific way, and it was easy and very nice experience. Also, there is Hubris, which is RTOS that is resistant to driver crashes. It is quite complex topic. I gave a talk on it during our Rust meetups, but I recommend you to just read the documentation because I was not as convincing as the company behind it is, I believe. Yeah, that's more or less what it is about it. And just one thing, if you think that it is not mature enough to incorporate it into your hobby project, let me tell you that it is ready for mission critical, because just a few weeks ago, safety critical approved. If you know about safety critical market, SLD is the highest guarantee on reliability. So basically, from now on, you will soon be able to write Rust in extremely critical systems like your car's ABS system, for example. So I think if it is already there, it is mature enough for you to give it a try. That's all. Thank you all. It was a pleasure for me to tell you about it.
Is there any questions?
Hi, thanks for your talk. How would you compare peripheral access crate to a device trees found in some other embedded operating systems?
Oh, device trees. So peripheral access crate is just the memory layout itself, where device tree is more like how do you configure your peripherals. So peripheral access crate is just set of definitions. I would be more in favor of comparing device tree to hardware abstraction layer crates, because this is where you do the actual configuration. But yeah, it is very different approach, more classic to microcontrollers, I would say, where you just write an initialization code by hand instead of having a config file.
Okay, thank you.
Any more questions?
You mentioned that it's already ready for the Rust is already there that you can use it for your hobby project.
Mhm.
What are some of the projects that you have actually used embedded Rust for?
Yeah, so I can tell you about the project I am developing right now. So I have a floor heating system at my home, which is not working as nice as I would like to. So, long story short, I just started developing a smart home project. And yeah, I hope to publish it sometime, but I do it in Embassy, by the way. And I think I will just wait for async function in traits to land in stable Rust before committing to a project like this. Yeah.
How about professional projects?
About professional projects. So I write Rust full-time, but these projects are Linux user space applications. So this is not the same thing.
You showed this Artic example with tasks, right? Was it async? It was before, right? Yes. There was an async event,
Yes.
or
Yes.
yes, but there's nothing asynchronous like await happening in here, right? Even though I would presume that for the
Yes.
on log there would be some kind of await.
Yes, but this is so in previous versions of Artic, there was a monotonic timer that you could, for example, just spawn a task after some time. But they got rid of it, and what they did instead is they have like a monotonic timer that you can asynchronously await on. So there is not a lot of support for async in Artic, but they decided just to go with async keyword and just move things around. There is not a lot you can do in asynchronous way, unfortunately, in Artic so far. This is just for delaying.